reduced to copper elemental. So that means copper elemental would be a reducing agent. Do you see how it works? Ox plus N electrons yields red. It's real easy to identify what the oxidizing and reducing species are, if you remember that. Learn it right the first time. Why do the anions want to flow that way? What am I producing in here? Cations. So you don't have charge inbound. What am I consuming over here?
The ions.
Cations. So that's why the cations want to go that way. Does it make sense? Look at the pattern and learn and know the logic of it. Shh, don't tell him any of this stuff. Now, let's look at this setup. If this is my electron flow, what does this have to be? The anode. In a galvanic cell, the electrons always come out of the anode and they are consumed at the cathode. Oxidation always occurs at the anode, whether it's electrolytic or galvanic. Okay. Now, this is my net reaction. Copper elemental and silver ions produce copper metal, copper ions and silver metal. Question: could I force this reaction to go in the reverse direction? Can the reverse reaction occur? And in this case, yes, it's a reversible reaction. What would I have to replace the voltmeter with?
Something that runs electricity.
Which direction would the current have to flow?
To the left.
The opposite way?
Yeah.
That's what I want you to say. If this is going the opposite way.
Would it have negative volts? Sorry.
Yeah, you can think of it that way, yeah. But if I pump electrons in this way, where are electrons going to be consumed?
With that with the copper
ion going to
around.
copper metal. Now, the copper ions going to copper metal becomes a what? Copper ions plus, that's
the reduction.
That's the reduction reaction. So what does the anode compartment become?
Cathode.
The cathode. And what does the cathode compartment become?
Anode.
The anode. But I keep this same sign because that way I know it's an electrolytic cell. Okay? This is how your different reactions, but the batteries in your cell phone, when they go dead, what you're doing is you're forcing electrons in the opposite direction. You're reversing the process that happened at the anode. You're forcing it to become the cathode, and you're building up more of the species that you consume in both sides.
Wait, so what's like the other ion species with lithium in like a modern battery?
I somehow neglected to memorize that.
Okay.
It's graphite.
I somehow I didn't
Okay. I thought you
memorize
might
it.
know.
I don't know it off the
Okay.
top of my head. But do you see how this worked? Now this idea here, this porous plug, it can be a ceramic frit that's semi-permeable membrane. You can fill this whole thing up with sodium nitrate solution and use agar to make like a gel out of it. Remember making petri dishes with agar? Do you ever do that? You ever make Jell-O?
Mm-hmm.
Yeah.
It's like Jell-O with salt in it. It will conduct electricity. So the ions are free to move throughout that gel. Okay? But this just completes the circuit. And what's going on running it this way, I'm using up copper elemental and forming copper 2 ions. Here I'm using up silver ions and forming silver metal. If I let this run, eventually the voltage would go to 0. I would use up maybe all of the silver that's in here. And if I wanted to recharge it, if I pump electrons in the other way, what would I be producing over here? The opposite reaction is going to occur if the cell's reversible. So the cathode compartment, if this is the galvanic cell as written, if I make it electrolytic and recharge it, the cathode becomes the anode and the anode becomes the cathode, but we keep the same sign so we know it's electrolytic. It's not producing voltage, we're doing work on it to make the reaction go in reverse. That's the logic behind it. Got it? Now, let's look at what's going on in this battery. This is just going to be just a general setup. What's going to happen to the amount of copper that's here?
It's going to decrease.
Decrease. What's going to happen to the metal over here?
Increase.
Increase. And you don't have to have the electrode changing size. You can have a species in solution that migrates to the electrode surface for the electron exchange. So let's just take a look at this. It starts at the anode, electrons are lost there. They go through the wire, set the load on fire. They enter the cathode and reduce the cation.
In a voltaic electrochemical cell, an oxidation occurs at an electrode called the anode. The electrons released at the anode travel through a wire to another electrode called the cathode, where the electrons are
Pieces are coming
consumed
out of
in a
this
reduction
side,
reaction.
being laid down on that.
Anions are then shuttled through a salt bridge from the cathode compartment to the anode compartment. Otherwise, a net negative charge would build up in the cathode compartment. The negative charges move in a circuit through the cell.
What they're showing you is externally, electrons are moving through the wire and then they're consumed here, and then anions are going back. Just to complete that circuit. Okay, does this make sense? So over here, I'm putting stuff into solution. Or I'm making a new species in solution, and we'll see that in a bit. Electrons move from the anode to the cathode in the wire, and anions and cations move through the salt bridge. The anions move towards the anode, and the cations move towards cathode. Now, this is where you may get a little bit messed up. So let's take a look at what we're saying here. So far, since this is my anode and the oxidation's there. What's up?
Thank you for the lunch money.
Oh, okay. I would have forgotten about it because I already had. You should have, here, you want to keep it?
No, I tried to get to Miss Bagger. She's like, he won't take it. I'm like, oh, he'll take it.
No, I wouldn't either. She forgot her wall one morning. Anyway, what is being reduced from that copper electrode? Didn't we make copper ions?
Yeah.
So what was being reduced? The electrode itself.
Yeah.
Could I have iron 2 going to iron 3? Isn't that a loss of electrons, iron 2 forming iron 3? So the iron 2 could travel to the electrode, if it's an inert electrode that's not reacting, and form iron 3. But that's still a reduced species making an oxidizing species. Does this make sense? So I'm producing the electrons, they're going this way, and they're getting consumed over here. And what we were looking at, we had the silver ion getting the electron and making this silver electrode bigger. If it's an inert electrode, I could have iron 3 gaining an electron to become iron 2. And that exchange, the point is, the electron exchange always occurs at the electrode surface. Electrode loss has to occur so that it can go through the external wire. So that means that happens at the electrode surface. The pumping out of electrons and the consumption of them always are going to occur at an electrode surface. And here's my anions going towards the anode and cations going to the cathode. And in the anode compartment, oxidation occurs. In the cathode compartment, reduction occurs. Catch the lights for me, please. Don't catch the lights, turn them on.
All three
I
tracks.
tried to catch the lights, but they were too fast.
Is that all right?
Yeah.
Okay.
Now, let's look at this. In the anode, we had the zinc forming zinc plus 2 and 2 electrons. The reducing agent gets transformed into an oxidizing agent and kicks out 2 electrons. And guess what the preferred direction is? Strong to weak. And then over here in the cathode compartment, we have reduction. So we have the oxidized species in solution is gaining an electron to become a reduced species. Okay? This oxidized species is undergoing reduction because it's the oxidizing agent undergoes reduction to form a reducing agent. And over in the anode compartment, a reducing agent undergoes oxidation to become an oxidizing agent. Does that make a little more sense now? So this is what the Galvani and Voltaire played around with these goofy, these are early batteries. And they were used more as novelties. Let's see if we can make the frog leg jump. Let's see if we can make Uncle Elmer jump, for party games and such. Because they didn't have flashlights, they didn't have cell phones, they didn't have anything to plug stuff into. And this is cell potential, E0. Look, what's this? That's the concentration of the zinc ions. And this is the concentration of the copper ions. Electrons are driven from the anode to the cathode by an electromotive force. It's a push. And we're going to find out that we can relate that to delta G. For zinc copper cell, this is indicated by a voltage of 1.10 volts at 25 degrees when the concentration of zinc and copper are 1 molar. So this is implying that there's going to be some kind of a dependency on concentration. Yes?
Do the concentrations of the two ions have to be the same?
No.
Okay.
And as you're running a battery, they change. For copper zinc, the cell potential is 1.10 volts at 25 degrees when zinc and copper ions are 1 molar. This is the standard cell potential E0. Guess what the concentrations of all species has to be to get an E0? 1 molar. Okay, guess what the temperature has to be for E0? 25 degrees C. Guess what the pressure of gases has to be? 1 atmosphere. This cell potential is a quantitative measure of the tendency of reactants to proceed to products when all are in their standard states at 25 degrees. If it's junk in solution, it's 1 molar. If it's a gas, it's at 1 atm. Are we good?
Yep.
I don't want to do anything more today. Also, you do realize what you have to do for that phosphoric acid lab report? That should take
Yeah.
how long to do?
20 minutes.
Thank you.
Standardizing one took me like 5 minutes.
Yeah, I just want to do that tonight.
Oh yeah, I could give you the data table because remember we did
I work.
Oh,
standardizing
yeah.
there.
Is that due?
But There's a second
Or
part to
can,
it,
yeah.
so
Okay.
but I could send you the first part since we have the same thing.
Well, he wants it by Monday.
You know the standardizing that? Or the standardizing animation and all of that? Yeah, we're standard the option to like, yeah.
Look, I got so much junk to grade right now, it's like, and I was just caught up this week, and it's like, oh, what the hell in a handbasket again?
Yeah, I thought you were caught up.
I was. They keep turning more crap.